Hi everyone, welcome once again to the webinar that we have today on can we use mixture models to predict market bottoms. Can anyone hear me? Can everybody hear me please? Could you confirm? Perfect, great. So we're going to start the webinar now on can we use mixture models to predict market bottoms. To take the webinar today, we have one very special guest. He is Brian Christopher. He's a quantitative researcher, Python developer. He's a CFA charter holder and the founder of Black Ops LLC, which is a quantitative research firm. 6 years ago, he learned to code using Python for the purpose of creating algorithmic trading strategies. 4 years ago, he self-published his research with a focus on practical reproducible application, so that he could share his experiences with coding and his experiences with research, and he published it to share it with everyone. Now he continues, his open research initiatives for a growing community of traders, researchers, developers, architects, engineers, and practitioners across various industries. He attained a bachelor's in science in economics from Northeastern University in Boston, MA, that's Massachusetts, and received the CFA designation in 2016. So ladies and gentlemen, I would like to welcome Brian Christopher to take this webinar. Brian, can you hear us?
Hi, I can hear you. Can you guys hear me?
Perfect, Brian. Yes, we can hear you. So I am going to hand over the presentation rights to you so that you can share your screen and take us through this webinar, and I hope we have a wonderful webinar today. I'm going to start giving you the presenter rights, and the stage is yours.
Well, thank you guys. I appreciate everybody for taking the time out to come to this webinar. It's my first, hopefully it won't be my last, so please bear with me as I get my bearings. So originally I started down this path because my research, of course, most people in predictive analytics, you start with time series analysis. But one of the problems that I found repeatedly was that traditional techniques that we use with time series analysis requires that your data be stationary. And that's a pretty strict requirement, especially in terms of asset returns, where we observe multiple phenomena that violate the rules of stationarity. And so, in my experience, I haven't had a lot of success using these techniques to predict returns or to, I guess, to time the market. So that's kind of what I felt like we needed to address. This is just a quick graphic. I'm not sure how many of you guys are familiar with stationary versus non-stationary time series. But one of the things that you find is that stationary time series, you don't want trends in the time series. You don't want the variance to change over time, and you don't want the asset returns to be serially correlated. But as we see in practice, though, that's often not the case. So what can we do? We need a model that doesn't require stationary data. We need a model that can approximate nonlinear distributions. So during this process, I came to learn a little bit more about mixture models, and it was very interesting. So they're built on several established concepts. Now just briefly touch on them and then move on. Markov models, so those are sequences where the future state of the process only depends on the current state, so there's no memory. Hidden Markov models are sequences where we don't really know what the true state is. It's unobserved. So we have to use other observable factors that we hope give us information about the true state. And then the expectation maximization algorithm. So that's a class of algorithms that iterates between computing class parameters and evaluating the likelihood of the data given those parameters. So with that out the way, let me see. Go to the next slide. So how does this apply? Well, we know that time series overall, they exhibit temporary periods of stationarity where the expected means and variances are stable. We can look at these hidden states or these temporary states as a form of a regime. So if we can better estimate an asset's most likely regime, including the associated means and variances, then our predictive models are likely to be more adaptable in real time. So just to hammer this intuition home, we think of an asset's returns as a sequence of states or regimes. Each regime has its own mean and volatility. So a simple example in some of the literature that I've seen on this topic, looks at low volatility versus high volatility regimes, and then tries to estimate, which one are we likely in. And if we're in a high vol regime, then, you're going to be more risk averse. If you're in a low vol regime, you're going to be way more risk seeking. So the model also assumes that over time, the asset's returns will transition between these regimes based on probability. What makes a mixture model so powerful is that they try to estimate the sequence of these regimes, the most likely sequence, and calculate each regime's descriptive attributes, the mean and variance, and the probability of transition between these regimes. So it's a very, very powerful modeling framework in theory. So the most well-known is the Gaussian Mixture Model. And it gets that name because it essentially assumes that each regime is generated by a Gaussian process. So, the low vol regime, the high vol regime, they're both, generated by a Gaussian process, a stochastic process. So the model uses the expectation maximization under the hood to calculate the probabilities, calculate the regime parameters, until convergence or another stopping criteria is met. So as an example, this is the SPY ETF. I fit it with 3 components. So that's one of the assumptions that goes into the model. You have to tell it how many regimes or components to look for prior, which is very similar if any of you guys have a machine learning background, very similar to k-means. So in this example, we looked at low volatility, neutral, and high volatility regimes. And so you see it color-coded it, so you can kind of see how the model views this time series. Here's the model output for this time series, in that the values that I've highlighted represent the asset returns regimes, the mean and variance of each regime. And so we can see that it has classified each one in a fashion that we wanted. So we see that the secondeth hidden state has a negative return, negative average return, and the largest variance. So this would definitely represent our high volatility regime. The 1th hidden state looks like the low vol. and the 0th is somewhere in between. So essentially why I'm showing this example is to demonstrate whether or not GMMs, Gaussian mixture models, can model non-stationary data sets. Well, we can see that it handles it by design. We've already broken it up into several regimes with various means and variances that allow us to isolate areas of stability or likely stability within a non-stationary time series. So I thought that was pretty powerful. Oh, this is a wrong header, but the question here that I'm trying to demonstrate on this slide is whether or not GMMs can approximate nonlinear data distributions. And so here I show an example where we use a function from Python scikit-learn called make moons, and essentially it just creates these nonlinear data sets, as you see. So when we try to fit fit the model with just two components, you can see that it doesn't really approximate the data very well. So what if we try to fit it with a lot of components? So the bottom slide shows the distribution fit with 16 components, and as you can see, it's able to approximate the shape and the distribution much more effectively. Let me see. Missing a slide. But what this also does that I don't have here in this slide is that the GMM 16 allows you to actually sample from the fitted model data that literally mimics this the bottom slide. So we can draw, for example, 500 new data points, and they will approximately look just like the Make Moons data set. So essentially, GMMs can approximate nonlinear data sets. So we can see that they overcome several of the weaknesses of traditional time series analysis models. So the next step in this process I looked at was, all right, so let's design a toy strategy or an implementation to see if this is a worthy path of further research. So the strategy design uses a total of 4 factors to estimate the sequence of regimes and the parameters. So we use the assets returns and that's from Yahoo Finance. We use the TED rate, the Treasury, U.S. Treasury 10-year, 2-year spread, and the U.S. Treasury 10-year, 3-month spread, and that is available through the Federal Reserve database where they publish all their data and metrics. So the general overview of how I design the strategy, and I'll show a little bit of code as well if people want to see that to kind of show how I broke it out. But essentially the strategy works as so. We take the data, we feed it to the GMM, we fit and then predict. We use the fit and predict method to extract the estimate of the last regime label, and we need that label so we can get the model estimate of the mean and variance for that particular regime. Now, this is kind of the unique part of this strategy. We feed the parameter estimates of the mean and variance to the Johnson SU distribution. not the normal distribution, the Johnson SU distribution. And then we draw, in the strategy, I draw 1,000 samples, but, it could be, whatever, amount you want. We draw in samples to construct our 99% confidence intervals. This strategy, by definition, assumes that any actual returns that fall outside of those confidence intervals are outliers and assumed to mean revert, especially returns that fall below the lower confidence interval. So this strategy essentially looks at the returns post the outlier event, in a sense, assuming a long only or a buy of the ETF for a number of days after the outlier event. So here we go. And so for an example, this is an example output from after we run the model, run a little bit of the evaluation, and then the model plot. And this one was for SPY. And we can see how the confidence intervals, or how the model estimated the confidence intervals. One of the things I like, especially about the way that I really like the way that it adapts to the kind of changing volatility, the volatility clustering. It's not straight across the time series. It does have some adaptive capabilities. And as you can see in this particular example, the accuracy overall was around 73%. However, when we look at the equity curve, it leaves a little bit to be desired, especially versus a buy and hold strategy over that time period. Okay. So to further evaluate this strategy, we can look at each one individually, but that's really pretty slow. So one of the things that I had to do, that I had to do was organize the data appropriately in a fashion that's called tidy data, and it makes it really easy to look to analyze the results in a number of different ways. But I can, I'll show you some that I've done. I made the data sets available on GitHub, and I encourage people, if they're interested, to play with it themselves and see what their results are as well. But we can evaluate each ETF individually, or on the ETFs collectively across lookbacks. And so in this strategy, I look back at 1 year, 1 year, 3 year, and then an expanding window. So 1 year, 3 year, and an expanding window. We can look at across the steps. And when I say steps, I mean how many periods after the outlier event. And so in this case, steps represent days. So we look at, I believe I did 1, 2, 3, 5, 7, 10, and 21 days. Or we can look at these results across the Ks, meaning the number of components or regimes. So we'll look at a few examples in the following slides. Okay. So here we have a facet grid where we have broken out each ETF that I've looked at. You see it's color coded by the look back. 999s is the expanding mean, or the expanding data look back period. So it basically just uses much data as was available in a walk forward fashion, whereas look back one only 1 year of data, 3 years of data. And so we can see the kind of distribution of median returns per event by for each ETF. And here you can see that we have the vertical line indicating where 0 is. And so one of the things that jumped out to me at first glance was the outperformance of SPY, QQ, TLT across the look back dimensions. We can see that EEM, EFA, GLD a little bit more symmetric in their distribution across look backs as well. So, and here we do the same thing, except we look at a value called the sum ratio, and essentially what that was it'll probably be easier to show. Let me see if I have this up available. I did. Where is this? All right. Well, I'll come back to it maybe in the question time period. Cannot find it right now. The sum ratio, though, just looks at for each individual ETF. We sum up the total returns of every event that was greater than 0, and divided it by the sum of returns less than 0. And so any value greater than 1 is considered a success, meaning that our strategy, given a buy over every outlier event that fell below the confidence interval, the sum of all the buy-ins ended up positive. The ratio of positive to negative with greater than 1 again is a success. But we see the outperformance relatively from SPY, from QQ, from TLT, and again a more symmetric distribution among GLD, EFA, EEM. And so in this example, we can look at the median return for each ETF, again color-coded by look back, and across the step dimension. So how many days did we hold this particular ETF, or how many days did we evaluate the returns after the outlier event? And again, we see similar outperformance from SPY, QQ, and TLT across all steps that I looked at. But again, one thing though that I need to point out, the longer your holding period, of course, the more exposure you have to the market, and so the results tend to become more intermingled with just the general trend of the market. So I'm not sure, or at least I haven't isolated in this particular study, how much of that influences especially the results of SPY, QQ, and TLT. But I was actually kind of surprised to see EFA do well relatively across the step dimension for various look-back periods. Okay, so now here we look at the sum ratio again. And it is greater than 1 across multiple dimensions. So again, this is looking at the steps. How many steps do we walk forward, or how many days do we hold, or is our holding period? across the look back dimensions, how many ended up positively, was the strategy an actual success from holding, or buying in at the bottom. SPY, triple Q, TLT do very well. GLD, it looks like it really depends. I mean, it hugs the break-even line, but really depends on the variables in terms of the number of steps or the look-back period. And then EEM, we see does pretty well with the longer look-back periods across less steps. So for EEM, we can see that if we hold it for, using this strategy for long periods of time, the performance degrades substantially. Same thing for EFA as well. So here we can evaluate the median returns across K. And K, again, is the number of components. And we can see a similar pattern again emerge. SPY, triple Q, TLT do very well across look back dimensions and across Ks. And so you can see that we, in this particular study or research, I looked at 2, 3, 5, 7, 9, 13, and 17 and 21 different components, feeding the model to fit the or predict the asset return distributions. So again, SPY, triple Q, TLT do very well. EFA does pretty well also, and GLD shows some promise, although it does look like it does much better with the expanding look back period versus 1 or 3 year, whereas EEM is all over the place. But it looks like EEM does very well, a lot better with less components. So maybe as more components get added, there's maybe some overfitting for EEM, but definitely something to look at. So again, we look at the same type of setup except for the sum ratio. SPY, triple Q, TLT do very well. GLD, again, depends a little bit on the parameters, but shows pretty broad success. EEM, similar. EFA looks like it struggles here in terms of our actual, total outcome of the sum ratio. So I'm just going to say the conclusions, and then I'm going to go through a little bit of the code, or just kind of talk about it high level. And then I believe that the guys at QuantInsti will come in and talk a little bit, and then we'll get to the questions. So one thing I noticed, and I can show a quick graphic on this, one of the secret sauce for this in terms of this strategy was the choice and return distribution. So the proper sampling distribution. If we use the normal distribution in this setup, it just never adapts to the variability of the asset returns. The variance is never wide enough to encapsulate it. So that was something that really stood out to me. And I'm not sure how many people are familiar with the Johnson SU distribution. And I wasn't familiar with it before I started this project. So that was really interesting. Hold on, this slide needs to be a little bit updated, but the success of the model, I don't know if it's wholly measured by your measure of success, but in terms of what we saw, broadly speaking, looking at the sum ratio, the strategy overall, I thought definitely is compelling. We got at least 3 US-based ETFs that show pretty significant, or at least worthy performance, worthy of further investigation, including, across various dimensions. We saw EFA do pretty well. We saw EEM do decently across some dimensions, and we saw EEM do decently across some dimensions as well. So overall, in terms of the success ratio I was looking at, like I said, was the sum ratio, and overall I think that showed that the GMM as a framework for asset distribution or asset return distribution prediction could have or has merit. It was consistently successful with SPY, QQQ, and TLT. But like I said, I must note that there are strategies that performed as well or better by simply being long the U.S. market post 2009. So again, we always have to keep that, temper our expectations a little bit, keep those things in mind. So now I'm going to go to a little bit of the code for, any of the Python people out there, or coders out there who are more interested in how I set that up. Let me go to, so here's the model runner class. And this essentially just takes the data and the parameters. I created a little convenience function called run model, and you can see the setup. Nothing too complicated, just building on simple concepts. Here's where we implement the Gaussian mixture model and components, some of the other default parameters. If people are interested, there is a Bayesian Gaussian mixture, and that's interesting because you don't actually have to tell it the exact number of components. It can learn the optimal number of components from the data. And then as I discussed earlier, this is kind of the flow. Using the predict method, we get the estimated hidden states. And then from the hidden state, we extract the last regime. And then we get the model, the estimate of the mean of that regime's mean and variance. And then we feed it into our sampling distribution. And so I kind of glossed over, but the Johnson SU distribution has 2 shape parameters that make it so much more flexible than some of the other distributions I've worked with, called A and B. I found those parameters just through a coarse search. And then here's the prediction cycle. So you can see that the way that this model is implemented is in a walk forward fashion. So the model does not look at, I tried my absolute best to ensure that there was no look ahead bias introduced into the model. And so anybody who is really into the code, feel free to go to my GitHub link and kind of tear it apart. See if you can identify any errors. Be happy to for your feedback. But this was the basic structure. This is called the model runner class again. So that was the basic structure for the estimation model. And then essentially what the what my research did was loop this over and over again across multiple dimensions. I also created a convenience class to evaluate the results as well. I won't spend too much time with that, but that's pretty self-explanatory. One thing I wanted to also mention was that the data that I used, I made available as well on GitHub. So the mixture model merged data. So that is all the ETF price or return data and all the FRED data together in a what's called the HDF5 format. This format I found to be really good. It's very fast read-write speeds for large data sets. I think it was designed for you know, astronomy data sets, you know, really large big data, numeric data. So that's what that format is. But that data's there. And then I also outputted the results of the aggregated mixture model results across all dimensions. Again, so feel free to play with that data. Here, I'll show you an example. And so you can see when we load up the data, so that was to output it, but here's the data. We can, when it's organized this way, I mean, there's a lot of different ways we can chop it up and look at it and try to figure out whether or not this is actually a worthy strategy to continue researching and developing. And in this example, you know, we can isolate SPI, we can group by the number of components, the number of steps, 1 day, 2 days, 3 days, and the look back period. We can look at the means of all these metrics that I output, and again, you can look at, where's this? So if you want to see what those metrics are from the coding perspective, it's right here in the results eval class. And also, you know, feel free to ask any questions. I'd be happy to answer them to the best of my ability. Even post webinar, feel free to contact me. But we can see that we can really slice it up as we want. We can get as granular as we want. You know, we can play with you know, the table formatting. This is, again, looks at the similar setup, except this one is the sum ratio specifically. And so we can see, you know, across a lot of dimensions for SPI especially, that there weren't too many times where the strategy had a collection of parameters where it did not end up positive in the end. And you can tell by the fact that so many of them are greater than 1. And so we can also evaluate it on an aggregate level as well. And this is just some plots that I created using this data set. But, you know, this is all here uploaded to GitHub. Feel free to explore. Oh, one thing I wanted to mention before we get out of here. So why did I use the Johnson SU distribution? So here's a sample output from early in my research. You can see that it has a lot of the characteristics that I said or that we, you know, determined was required for a modeling framework that would supersede traditional time series analysis. And here we can see that the confidence intervals really do a good job, I think, of adapting to the changing volatility of the return series. You know, getting smaller when it's not as volatile and getting wider when it was. And for comparison, here's what happened with when I did the same process. Only thing I changed was the normal distribution, and we see that the accuracy plunges dramatically. Although maybe counterintuitively, if we look at the equity curve, the Johnson SU distribution, it was pretty good here. But then we see the normal distribution even better. But again, I think this is more a result of the fact that the accuracy was so bad, you're essentially long all the time. And as we know, if you got in at the right time in 2009, you could have just been betting everything, and you would have done pretty well just simply holding the market. So with that said, I will, you know, if you guys want to jump in and do your thing, and then we can go to the questions if there are any questions.
Hi, Brian. Thanks so much for such an informative session. Sorry about the delay in coming back online. I'm just going to take the screen sharing rights away for a minute, before we start off with the question and answer round. Just a small little thing that I want to discuss, and just give me a moment here. All right. So just wanted to talk to our audience about our company, that's QuantInsti. If you are looking to explore algo trading and learn how to research, devise, backtest, and evaluate different trading strategies, we do have a program known as EPAT. You can see our contact information on the screen, and you can actually give us a call or send us an email and talk to us more about EPAT. It's a 6-month program which includes 2 months of project work under an expert faculty who will help to guide you and take up exciting topics and projects, like some topics that were covered by Brian's webinar today. Also, I got a lot of questions asking whether we would be sharing the links for the GitHub page. Brian would definitely be sharing the links with us, and we would be sharing those links with you too as well in the email. Now, I'm going to hand over the rights once again to Brian. Brian, do take some questions. We've got some interesting questions in our chat, and hopefully you can solve some of the doubts that we have. Mr. Derek Wong has left us quite a lot of questions, and there are some questions from other participants as well. So I'm handing over the screen once again to you, Brian. The stage is yours once again.
So the first one I see, how did I determine the shape parameters for the Johnson SU distribution? Good question. I just went through a kind of a very coarse parameter search. Again, because the distribution was very new to me, I wasn't sure how the shape parameters would actually affect the prediction accuracy or the confidence intervals. So like I said, I just really went through just kind of experimenting broadly between values of 0 and 1. And when I 0.2 and 0.7 seem to be the most generalizable shape parameters that I found, without necessarily specifically engineering that result. I didn't grid search the result, so I'm sure there might be more there might be a better set of parameters there, but I did not I didn't grid search that. Let's see, what's the next? So I see a bunch of questions from a gentleman, Jim Hutchinson. Apparently he's left though, but he had a good question. How can you tell if the factors you selected are actually helpful in the GMM? The way that I was able to determine that through my research was, in fact, the model accuracy. So I tried a lot of different factors to kind of just get a feel for what was effective and what wasn't. And it just and so what I ended up ultimately figuring out, and this also I think answers one of Derek's questions about maybe the difficulty in the model generalizing as broadly as it did for SPY, triple Q, TLT, for GLD, EFA, and EEM. I chose U.S.-based interest, interest or fixed income metrics, and so that might be why it's a little more successful in terms of predicting U.S.-based asset returns versus maybe some commodities and or global ETFs or non-developed market ETFs. And again, I chose those particular factors because the bond market overall is much larger than the equity market in multiple ways. And so that's why I picked those. And I think that might have something to do with it. And so you know, a further area for research or for exploration would definitely be looking at combinations of other factors, or maybe factors that are more predictive across a wider range of assets. So let's see. Let's find another one. Richard asked, why was the GMM applied to returns instead of price? Isn't price the non-stationary series? That is, no, that is not true. Price is not stationary. And the problem, if you use price in terms of quantitative analysis, is that price is not scaled appropriately across all assets. So when you try to compare results or strategies that use price, or you try to apply these models on price, the scale, the variation in scale, you know, an example being, you know, a stock that's $100 versus a stock that's $5 can really alter and kind of invalidate your results. So that was that one. Let's see. GitHub link. Let me see it. Find another one. So adding look-back periods gives similar distributions by visual inspection. Does adding additional lags not give significant additional information? I'm not sure what you mean by additional lags. Are you saying longer holding periods or what? Not quite sure. If you're still here, feel free to follow that up if that question wasn't answered earlier. Here we go. So it says K factors almost all decline as additional steps are added for all ETFs. Does this have similar problems as lags not giving additional information, or is it a bias variance problem? In this particular study, you know, I'm not quite sure, to be honest with you, in terms of the K factors. So we only went up to 21. You know, could it do better with more factors? I would start to think that there's definitely a maximum number of components, and that issue would be related to overfitting. Because in theory, you could have enough, you could add enough components to arbitrarily, you know, approximate any data set, any asset return distribution. But would that necessarily generalize well into the future? Likely not. So again, that's another area of you know, further exploration and research to do. I see a question: is tidy data available for Python or just R? I actually don't know if that is if that's an actual package or not. I just know it as a concept for how to structure large data sets for easy or easy as well as detailed analytics and research on data sets. Is the use of lookbacks similar to backtesting? Yes. In one regard, yeah, you're choosing a set amount of data from the past to fit and estimate the model with the intent or hope that those you know, that will generalize well to the future, you know, for unseen data.
Brian, sorry to cut you off there. I guess we're getting a lot of questions. If you want, what we can do is, guys, if I will be sharing certain contact details with you. You can definitely take the contact details down and get in touch with us or with Brian as well and ask him all the questions, and he would be able to answer you on a personal basis. So Brian, I'm gonna be probably sharing a few more slides with these guys about different links that these guys can go to. Thank you so much for such a wonderful webinar, and thank you for answering so many questions for us as well. Thanks for your time today, and I hope you have a wonderful day ahead of you, and enjoy the rest of the week, Brian.
Yeah, thank you guys for having me. I really do appreciate this opportunity. I hope everybody who stayed and listened, who have questions, again, feel free to contact me off-site. I'd be happy to interact with everybody here. And again, thanks for your time. I'm very appreciative, and thank you guys for having me and putting this together.
Great. Thanks so much for your time, Brian. Have a good day ahead. Bye-bye.
Take care.
Well, algorithmic trading requires you to merge two traditionally disjoint set of skills. One is finance, another is technology. So you need to merge skills in finance and technology to be able to do algorithmic trading. So you need to understand the markets, you need to understand big data statistics to be able to design your strategies. But once you have designed the strategies, you need to also understand technology to be able to automate your strategies. So therefore, that is where the QuantInsti's education programs come into place. So we train people about the entire gamut of operations and skills required to be able to be a successful algorithmic trader.